Okay, hopefully this will be, since this is a small crowd, it can certainly be very informal. I will certainly field questions, so if you feel like you have a question and you want me to answer that, just let me know. Don't feel free to interrupt me because I can be long-winded sometimes, but I'll try to keep this as succinct as possible. So I realize that other people have, either you want to go home tonight before midnight. I'll try to finish up by 11. I'm just kidding. But the okay, I want to talk about Cosmos DB tonight. Take a tour of Cosmos DB. So I'm not going to be able to get like in the weeds on everything about Cosmos DB in an hour or even less than an hour, because truth be told, it is a mile wide and it is a mile deep, and you can talk about a lot of everything I mentioned tonight. You can talk about it in great detail. So I'm going to try to give you the grand tour of it without getting too much into the weeds on how every little minutia of it works. So there's a lot of ground to cover. So with no further ado, we'll start. It's a little bit about who I am. My name is Blaze. That is my birth name. I get asked that a lot. That is the name my parents gave me. I currently work for a company called Winelect as architect, and I am a Microsoft Azure MVP, so I spend a lot of time doing a lot of advocacy for Azure, and specifically Azure open source stuff, so and the Azure platform in general. But my kind of niche is more the open source stuff, particularly containers and a lot of the Linux stuff on Azure. But I'm perfectly happy to use Windows. Obviously, I'm using it right now. I function as a partner cloud solution architect with Microsoft as well. That's basically a program where I get called into Microsoft conversations as a supporting resource for Microsoft, but I represent Microsoft on some occasions, and I'm also MCSE on Azure, which is basically I pass some tests. That doesn't really mean much. And I'm online at the One Mule on Twitter, and you can email me at bstewart@winelect.com if you want to. A little bit of a company I work for. I work for a company. Okay, with no further ado, let's talk about Cosmos DB. So, what is Cosmos DB? Cosmos DB was launched in May of 2017. So, if you've been looking at it for about 2 years, that's about right. So, a little over 2 years ago, it launched, and it was originally launched as a product called Azure Document DB, which is a document DB was just originally a document database that did something very similar to what you might get at a MongoDB. So it's just basically a way to store JSON or XML documents in a database that you could query with a SQL-like syntax language. But they built on top of that by making it a multi-paradigm database. Now it supports key value store, column value pair, column family tables, which we'll talk about in a moment, documents, and graph. And they also incorporated a lot of the functionality with Azure Table API. That was originally in Azure Table storage, but now they kind of incorporated that into the Cosmos DB space as well. And so it supports that Table API as well. So it's got basically a paradigm for everything. It's just not a SQL database. So if you want, the traditional SQL databases, this is not the solution for you. This is for everything other than that, pretty much. So there's a lot of different database technologies out there, but this is the one that supports, non-traditional, not remote database management solutions where you have tables and indexes and all that kind of stuff. And Cosmos DB supports server-side programmability through store procedures, triggers, and user-defined functions, or UDFs. And it's got programmability. You can do it on the client side as well as the database side as well. So it's a multi-paradigm database that allows you to do a lot of things that you can traditionally do with those more table-oriented databases like Oracle or SQL Server, particularly around store procedures and triggers and functions. The difference here is they're not written in SQL; they're written in JavaScript. So for a lot of people that go JavaScript in a database, they kind of scratch their heads and say, "Why did they do that?" and that's because inherently it was originally designed to be is built on the document database, which was storing JSON documents. So JavaScript and JSON go together, so everything was written in JavaScript. And now it supports multiple paradigms. That just kind of got carried along with the actual technology itself. It's dynamically tunable. By that mean you can scale it on the fly, you can replicate on the fly, you can if you need this much throughput for these number of hours during the day, you can add that. You can put I need to scale up during the hours of 5 o'clock to 6 o'clock at night, and then and in the middle of the night I don't need that tuning, so I can scale it back down to my workloads. So it is dynamically tunable and scales on the fly without interrupting your services. It automatically partitions. So if you know anything about database partitioning, what it'll do is it will it'll spread your workload over across multiple storage nodes. So it improves your performance with a partition key. So basically, you say I want to partition my data on this key, and then what Cosmos DB will do is spread that data across multiple storage nodes so that it gets better parallelization whenever you actually do operations across that partition. And your partition key is something you have to kind of figure out what you want to use. And my general rule of thumb there is look at your data and kind of figure out how you want to query your data, and then based on that, use that for your decide on how you want to use it for partitioning around what's going to be the most optimal field for querying on. So that's usually like an ID field, or maybe a geographic grouping, or a regional grouping, or maybe by company if it's a multi-tenant application, or something like that. And that way you get better performance around a particular logical division in your data. It also has global scale. By that we mean you can use a single data center, or you can scale it out to multiple data centers. And I'm going to show you what that looks like when we go into a demo here in a moment, how easy it is to scale this. And it automatically indexes every field and everything. So you can build custom indexes, but every field in Cosmos DB is automatically indexed unless you tell it not to index it. And that way it optimizes the speed of querying this, so you're not constantly doing scans across documents. It'll go to the indexes, and then the query engine is smart enough to look at the indexes and then get your data out of Cosmos DB. Okay, Cosmos DB supports 5 different consistency models. And if you're not familiar with what I mean by consistency, imagine when you're doing a write to a database. And in traditional databases, you have what they call strong consistency. That means everything is encapsulated within a transaction, and it will lock the records that you're writing to until that data has been written to the data store and has been replicated to all the nodes on that particular database cluster, if you're running a database like that. That's called strong consistency, and that's what most people are used to when they talk about consistency in a database. It means basically that whenever you write data, everybody that reads that data will read exactly what you wrote in the order that you wrote it. So strong consistency guarantees that your data will only be read in the order in which it was written, and it will be that way across all nodes across the entire database. Well, there are other consistency models, and from most relaxed to least relaxed, we can talk about these whenever we talk about consistency models. I'm going to show you a little analogy that Microsoft does in the portal in a moment that talks about these different consistencies. But the loosest one is eventual consistency. But basically what this means is every time that you write your data to Cosmos DB, there's no guarantee that anyone will be reading it in the order that you write it. It will eventually be there, and it will eventually be replicated across the global all the copies of the data. But there's no guarantee that it's going to show up in all the in the order in which you wrote it. And eventual consistency, though, is usually good enough for most applications. It basically means that eventually everything will be consistent. But if I'm querying the same record that someone else is writing to, I might get their rights, I might not get the rights, depending on which data store node it reads it from. Now, with each level of consistency, it gets better with the writes. Consistent prefix means that the data will eventually be consistent, pending that there are no more writes, but reads will not be out of order of the writes. So this basically means that the reads will happen in the order that they're written to, rather than with eventual consistency, you can get the reads out of order. So that's the difference between consistent prefix and eventual consistency. So with eventual consistency, anything can be written, and I might not, if I do 2 reads against it, I might get an old data or new data, but eventually it'll all be the new data. With consistent prefix, it basically guarantees that the writes, that reads won't occur out of the order in which the writes happen. Bounded staleness is the next one that is a consistency model, and basically what this one is time boxed. Every write is time boxed, so you won't get any data that's older than a specific limit. So if I say I don't want any data that's older than 2 seconds, it won't be. I won't get any data that's older. It will wait for new reads up to that point whenever I'm talking about bounded staleness. So it guarantees that to be up to a specific number of versions behind writes, no older than a specific age. So basically, if I'm writing new data, then what I'm reading won't be any more than 2 or 3 seconds behind that, or whatever my staleness window might be. If I say it's 500 milliseconds, then I won't be reading anything that's more than 500 milliseconds old. Which for many people, that level of consistency is pretty good. It gets a little bit closer to a strong consistency. The next one is session, and session. This basically means that with my session, my connection to the database, I will always read the order in which I write. I can see my own writes. Someone outside of my session might not see my writes, but I will always see the writes that I have written. And so I get them in the order that I got them. They will always show up. If I write something in the database, it will show up in my read if I read it next. But there's no guarantee that other sessions will be able to do the same. And then strong consistency is the last one. It's the one I mentioned first. And it's the one basically that says it's replicated across all regions everywhere. And it guarantees that the writes that reads will be consistent with all the writes before, not before the writes are done, but after the writes are done. And there's a performance trade-off with all of these. So with each level of consistency, you go down each consistency model you adopt. The stronger the consistency gets, the less performant it becomes. Because the reason why is with strong consistency, you have to wait for the replication to happen. Same thing with session. You have to wait for the replication to happen. And if you have to wait for replication to happen, then there is a performance trade-off. So that means that the data doesn't become available until those writes happen, and so reads become slower because of that. And if you have a query against a particular record that's being written to, it'll just keep that connection open until that write is finished. Then it'll read the data. So there's a performance trade-off as you go down with each consistency model. Now, this is an important concept within Cosmos DB, and I don't want to understate it, because with consistency, you might be asking at some point in the future, why is my database so stinking slow? And if you go in and then you look at your consistency model and say, well, I have strong consistency turned on, and you ask yourself, do I really need that? You say, no, I don't need that. My data doesn't need to be strongly consistent. And you can set it back to a more relaxed consistency, like consistent prefix or eventual consistency, and you will automatically see a huge performance boost in your database because you relax your consistency model, and you can get your requests going back and forth more quickly. I tend to recommend that people just stick to eventual consistency until you have a reason not to, and for most people that's good enough. Until you have a reason to go to one of these stronger consistency models, just turn on eventual consistency, and then it's usually pretty good enough for a lot of applications. And if it's not, then you can go with something else. So let's go flip over to the Azure portal and look at I'm going to show you how you can scale Azure Cosmos DB and what this looks like inside of Cosmos DB. So I have here deployed an Azure Cosmos DB instance. Can you guys still see my screen? Okay, good. It didn't have the little red box around it, so I was making sure you could still broadcasting. Now this is the Azure portal. Let me blow this up a little bit. This is the Azure portal, and I have deployed in this Azure Cosmos DB. And I'm going to show you some of the features of this guy. Now, just a second ago, I was talking about consistency here, and I'm going to show you this slide since we're on that topic. I have my consistency model on this particular database set to eventual consistency. That's because this is the application I'm going to show you later in a demo is basically saying this is, yes, I did. I should be seeing the Azure Portal. Let's see. Let me sure I'm sharing the right screen here. Share. Share screen one. How's that? Perfect. Okay, good. I'm in the Azure Portal. Okay, I'm in the Azure Portal, and this is my instance of Cosmos DB I'm using for my demos tonight. So I clicked on essential the default consistency here. Now, while I was on the conversation, the topic of consistency, I set my default consistency to eventual consistency. Now, what this means is that if I set eventual consistency, that means my writes are going to look like this musical notation here. I have this red note, this blue note, purple note, this black one, green, and yellow, and other regions are going to read these all out of order depending on my consistency model that I have checked. So if I check strong consistency here, it's going to be, everything is going to look exactly across every region that I deploy it to. So eventual consistency could be any of that. It's just, something, eventually it'll be consistent. That's why it's called eventual consistency. My writes are going to happen in order, but I might read a red note, a purple note, a green note, then a black note, a yellow one, and a blue one. But notice that the black one was written after the blue one. If I go bounded staleness, it's going to look something. I can set different time boxes on my bounded staleness for how long I want it to the lag number of operations or how many seconds and so on. And it looks like this. Like a particular read and write would be consistently across a given region, but eventually I don't want to read any more than 4 reads behind that or 5 reads behind that, and it's going to look like that in a different region in Australia. So whatever it might be, then it's making sure that the order's the same, but it's different. But the lag is behind this the canonical one, which would be the writes happening in the U.S. East region. So you can kind of go into the Azure portal and click around and play with these consistency models, and you can use this graphic to kind of give you a depiction of what that looks like. And I like this because it does give you an analogy for what that's going to look like. But if you're not sure, just set it to eventual, and that's generally going to be good. That's going to be, for most applications, it's good enough. Especially in read-heavy applications where you don't have a lot of writes. But if you have a lot of writes and you need those to be in a specific order across all the databases and across every region, and it's for it's because you have for some reason that you need that strong consistency, you can set that to strong consistency. Again, I'm going to look at this is the replication. So if I wanted to replicate this data to any other Azure region that supports Cosmos DB, all I got to do is check it, and then when I hit check that, and then I hit save, it'll automatically start replicating my data to that other region. So you can see how easy it is to scale this globally. I can say I want something in Europe, how about East Asia, maybe Australia, maybe one in South America. I hit save, and as soon as I hit save, my data starts replicating to all those data centers in Azure, and I don't have to do anything other than just click this little graphic here, and it will start replicating to all these different data centers. So that's a really easy way to scale this within the context of a read regions across the world. So scaling this is very easy to do inside of Azure. And so that's kind of a tour of the portal. Another thing I want to show you, I'm going to show you later on, is Data Explorer, but this is kind of the UI for this. And this is gives you the ability to query something about Azure Cosmos DB, and it gives you a nice little interface for browsing your data. And we're going to dig into what this is in a moment. When we look at a demo later on, but I'm going to be using Graph Database for my demo. But this is the Data Explorer is the utility for doing ad hoc queries against your data. I can do Gremlin queries against Graph, but you could use SQL queries against the document database, and you can do Cassandra queries against this table store and so on. So depending on what paradigm you set your Cosmos DB up, depends on what this looks like. But all in all, you end up with a way to see your data visually as well as browse it inside the browser. And I can set up store procedures, user-defined functions, and triggers right there. And I can also use firewalls and virtual networks, bind it to that, and then I can set up alerts and other things with that. So that's a tour of the portal. I'm not going to get too down in the weeds on this, but I did want to show you kind of the consistency models and the replication strategies that you can do with Azure Cosmos DB. So I'm going to flip back over to the deck here now and dive into some of the different models that you can use on Cosmos DB with here. But first I want to talk about NoSQL, because Cosmos DB is a NoSQL database. So I like this little cartoon over here. It says, do you have any expertise in SQL? And you say no. There's pause and says, doesn't matter. Doesn't really matter. Just write expert in NoSQL and you'd be right. So if you don't know SQL or you know NoSQL, then you would be right. So you can ride that wave. I think the wave somewhat died down. It's kind of an expectation that developers know it now. But in any case, NoSQL is basically the paradigms that we're going to be covering over the next few slides. It doesn't stand for NoSQL because you use SQL and NoSQL. It's kind of confusing. It basically stands for non-SQL or not only SQL, depending on the context. But generally speaking, NoSQL databases are those synonymous with document databases. By that, we're talking about things like Cosmos DB or MongoDB or other document databases that like we're talking about tonight. And some NoSQL offerings on Azure, like the ones on Cosmos DB, use a SQLite syntax. So with Cosmos DB, you have two options. You can use the Mongo API or you can use the Microsoft NoSQL SQL API. And for the given document database, that's going to look different. But for the two that are available on Cosmos DB, you can choose the Mongo API or the document database API, and they both use a SQL, like a SQL database-like syntax for selecting documents and filtering and querying documents. So just a kind of an overview of what the difference between SQL and NoSQL looks like. And NoSQL is a non-relational database, while SQL database is a relational. Data is stored in tables, and NoSQL is basically a hierarchical documents with key-value pairs. So basically think of JSON documents versus tables. So or XML documents versus tables. And so it's two different ways of storing data. Both of them could be used for different things. And they both have advantages and disadvantages. It's not that one is better than the other. It's just different paradigm. NoSQL has a flexible schema. The properties can easily be added on the fly. As SQL typically has a strict schema, so you're bound to the schemas of the table. And data is all written ideally for data where the records are all the same fields. NoSQL gives you a great deal of flexibility, while SQL gives you makes you use the schemas that are written to the tables. NoSQL data is denormalized, while SQL data is normalized. Relationships are handled through joins, and NoSQL, relationships are handled through either objects that are represented by the hierarchies in the documents, or objects that link documents together. NoSQL is useful for complex data structures, while complex data structures and nested data, while NoSQL is good for highly structured data where you need to have cross sections of that data. Now, NoSQL scales very well horizontally. And what I mean by horizontal scale is it's easy to partition NoSQL data. So I can I want to store all these documents on this node and all these other documents on a separate node, and I have very strong separation between those documents. And even though they might be representing the same set of objects, it's easier to partition it because all the data is bound up in documents versus a table, which is a lot harder to partition. Now, modern SQL server has some partitioning capabilities that you can put into it, but it's a lot harder to do it. A lot harder to partition your data in a SQL context than it is in a NoSQL context, but it scales better vertically. By that I mean you can adding new compute resources makes this one perform better. Now, NoSQL has ACID compliance. That gets back to all the consistency I was talking about. The compliance, ACID compliance depends on the technology, and NoSQL that is compliant. I'm not going to get into what ACID means, but it's a database. It basically talks about the consistency being bounded up inside of the transactions that you do, and depending on the technology that you use, even with Cosmos DB, you can be ACID compliant with Cosmos DB if you set strong consistency. SQL is always going to be that way. It's just the nature of the technology, and And NoSQL is good for useful for growing and changing data environments, where SQL is good for query heavy environments. So NoSQL is not real good for doing the heavy lifting on reporting. So I would, if I was going to do any kind of reporting against a NoSQL database, what I would do is I would take the data out of a NoSQL database, run it through an ETL process, and transform it into tables so I could actually do queries against it. And then, so if you need to do a lot of reporting against it, NoSQL is not going to be very good for that, but SQL is great for that. So what you could do is take a NoSQL database, run it through ETL, and put it in a data warehouse, and then run reports against it to your heart's content using SQL. And that's one way to do that with to kind of mix these two technologies. It's not an either or. It's usually both and proposition for a lot of different applications. Again, NoSQL is not a replacement for it. It's rather another tool for a different kind of job. As I mentioned, NoSQL performance and SQL performance depends on the kind of workloads you're doing it. So anytime you see metrics that are comparing SQL to NoSQL, it's like comparing apples and oranges. It's not parity to one another because they're two different technologies, two different tools. It's like comparing a screwdriver to a wrench. They can't be compared to one another. They both can be used for similar jobs for tightening screws or tightening bolts. But at the end of the day, one's going to perform well in some circumstances, and others are going to perform well in others, just depending on what you're doing. And the technology stack does not determine the data store. SQL and NoSQL can be used for most popular development platforms. So, in other words, if you're using .NET, you don't have to use SQL Server. You can use Mongo. You can use Cosmos DB, and vice versa. SQL Server does not prescribe that you use .NET. It does not prescribe that you use Java. It doesn't prescribe that you use JavaScript or for Node.js. So you can mix and match your development, your language of choice with your database technology of choice. And so you can mix and match those depending on the application. The main thing is trying to figure out what application database technology is going to be the best data store for the data that you're storing in your database. Just to mention that the data store, we've already looked at this. Database can be distributed across multiple regions in this. Geofencing can be applied. That's a really cool technology with Azure Cosmos DB. So if you need data sovereignty rules that apply to your data sets, you can say, I need my data in Western US, and I can't replicate that to Europe because they have all of the regulations that the EU is imposing about data sovereignty rules. So I need to make sure that I'm not storing data there. And I can put geofencing around my data as well, so I can make sure that certain data doesn't replicate to certain regions, but other data does. And I can also do read-write between regions by policy. This can be policy-driven too. And we saw just a minute ago when we were in the portal just how easy it was to distribute data just by going on a map and clicking a region and saying, I want to replicate to that region. This is an outdated map here. It's actually, because Cosmos is now supported in multiple regions in Europe and more in East Asia, some in South America, and even one in South Africa as well. So there's more regions that are coming online all the time with Azure Cosmos DB. And the distributed data provides 4 nines SLAs with 15 millisecond latency. So it's very fast, and it provides high-level SLAs. 4 nines is almost unheard of with any database technologies. So it's very robust, very reliable, and very performant when it comes to the SLAs and the performance SLAs and the uptime SLAs that they're providing through Cosmos DB. Document DB versus Cosmos DB. This is the document databases that you have available inside of Azure Cosmos DB. Document DB versus the Mongo API. They're kind of two tools that solve the same problem. It just depends on what you're doing. If you have an existing application that's already using Mongo and you want to lift and shift that, MongoDB. If you're starting greenfield, it's a little bit more. It's a little bit more less clear which one of these to choose. Mongo's got a very rich API, while DocumentDB is a more simple querying language. DocumentDB supports, this is the document database API, the SQL API as it's sometimes called. It has user-defined function store procedures and triggers that are available. You can do those in the Mongo API, but you can't directly leverage those in the Mongo API inside of Cosmos DB. So you can't call a Cosmos DB store procedure from Mongo API, but you can actually have them in the Mongo API because you can actually browse the documents and put those in there, but they wouldn't be available to you for querying in the Mongo API because Mongo doesn't support that. Transactions can be performed through server-side scripting to ensure ACID compliance, and this is one of those things if you want to do the you want to have ACID compliance, you can do that through server-side scripting, and it bottles that up in a transaction and writes that with the server-side scripting. And the document on Mongo, it's at the document level. So basically, you're writing everything in the document, and it does at the document level. You can't do that at the transaction level. So it just depends on which one of these consistency models you want to do that. The atomicity is at the document level, while at Mongo, by document DB, it's at the transaction level. So if you need to update multiple documents in document DB, you can create a stored procedure and then do it and then update multiple documents in the same transaction in a document database on MongoDB. I'm sorry, on the SQL API on the document DB from Microsoft. Document DB has a very robust security model, while MongoDB has very little in terms of inherent security. Basically username and password, but it doesn't have a lot of roles and responsibilities, while Document DB has very, very robust security model. And we'll look at that in just a second. The document database stores everything in objects like this. So we'll see things like it's basically a list of key value pairs that are arranged hierarchically. It looks like JSON data. I mean, that's really what it looks like. And again, we mentioned the two APIs, Mongo and SQL. And in Cosmos DB, keys can be defined based off partition. So if I want to partition my data, I can say I want to partition it based on first name, and everybody that has first name of Bob will be partitioned across the storage nodes. Or I can do it based on hobby or address, maybe it's by city or state or country. And I can do objects that look like this: network, edge network, external edge network, and so on. Basically documents that are JSON documents and represented in a hierarchical fashion with key value pairs. Now this is another type of storage that you can do in Azure Cosmos DB. Another paradigm. It's just a strict key value pair database. And this one is not a document database. It's just basically keys and values. And you can say data properties are arbitrarily. You can have any number of values in a key. It doesn't care what value you stick in there. This is key value pairs are supported through the table API, and you can have any number of keys that are defined as the partition. So basically, this is just a key value store pair column, a key value store where you can have any arbitrary data against a key, and you can have you can set essentially a partition and a partition key and a row key, and it will partition the row, partition the data on the partition key, and the row key will then be the actual key that is stored that you can look up at a row level, and then the value will be represented in that key. So the table API is what you need to use if you want to use a key value pair store for this. It does support some querying through an API called OData, and it's basically the ability to do some lightweight, where clauses, like where equals, where greater than on a given key, where row key equals 1, 2, 3, and you can query the values on that. So you can get filters or an AND operators, a lot of other operators that are using that OData API. And so this one's not as widely used on Cosmos DB. In fact, I don't know that I've ever met a customer that's using it yet. Mostly people use the document object, the document database, because it can basically do the same thing, but you have a document hierarchy. But this is available. That's why I included it in the slides. A column family database, this is a little bit different paradigm than most people are used to. A column family database is a collection of columns, really a collection of rows, and each row doesn't have a really strict schema. So this really isn't a table as much as it is. It's where any row in a given collection can have any arbitrary column. So I can say that my Bob column has email address and gender age, and my Brittany column only has email and gender, and my Tory column has email address, country, and hair color. But and if I wanted to query across these, I can query across all of these using the email address. I could query across all the ones using the Brittany and Bob row here. I can query across gender, but it wouldn't pick up anything from the Tory row here because it doesn't have a column called gender. So this gives me really flexible columns I can stick in rows, and I can query across those rows that all have a common column, and it will ignore rows that don't have that column. So it kind of gives you a way to have a table-like structure that's not bound to a really tight schema. And this really orients your data around the columns themselves versus having tables. So you can have any arbitrary data attached to a row, and the column becomes the more important queryable object rather than the row itself. And in Cosmos DB, the key is defined by a partition key and a row key. In this case, the partition key and the row key would be the name here, Bob, Brittany, or Tory. And then the columns can be any arbitrary column, and that can be queried against. And a column family database can be accessed through the Cassandra API. So if you have a Cassandra is a column family database that is put out by Apache and the Apache Foundation, and it is the one that does that supports this API. So if you have a Cassandra, it's used a lot in big data workloads that have arbitrary fields, and the Cassandra API can be lifted and shifted into Cosmos DB, and you can query it through that API. So this is very useful for, again, like I said, arbitrary rows that have arbitrary number of columns that can be queried across. This is one of my, and the last one I'm going to talk about tonight is the Cosmos DB, the Graph API, and this is one of the more interesting ones. And it is it's one of the more, because it's unlike something that most people have ever seen before, because it's neither documents nor tables. It's actually nodes and edges. So the data structure looks more like a web. It looks more like a social network, if you will, than it does a hierarchy of tables, or a schema of tables, or a hierarchy of a document. Rather, everything's joined together more loosely through relationships. So it's vertices and edges. So in this case, the vertices are these. Each one of these objects: Robin, Thomas, football, Ben, and the edges are the connections between them. Vertices, or the edges, are essentially your nouns, and your edges are the relationships. These are expressed as verbs. So laptop runs OS Windows. Robin uses laptop. Thomas knows Robin. Robin uses smartphone. Smartphone runs OS Android. So you kind of get the edges become your verbs. The actual objects become the edges. And then some common use cases with this would be things like social network, geospatial data, so things like logistics. So if you can imagine a map where each one of these nodes represents something like a city or a location on a map, and on that demo later, I'm going to show you later on, it's going to be using a map, and then or an IoT representation that I've seen where you have networks that are represented by edge devices, and I might have a camera, or I might have a sensor of some kind, like a thermostat, or an IR sensor, or I might have some kind of a microphone, or something that's collecting data in some environment, and that's all connected to an edge environment that's reporting back to some big data consumer. And IoT is one way to represent the objects in a graph database. Vertices are all these objects I have surrounded here. And again, they can have properties. So Robin has a name and an age. Laptop has RAM, CPU, and resolution. And I can express all of these as properties inside of my edges inside of Cosmos DB. So any object I assign as a vertice can have any number of arbitrary key value pairs attached to it that describe that. They're essentially properties of that object. And then edges are all these other ones. And these are expressed as verbs, and they can even have their own properties as well. And they usually express the relationships between the various nodes on the vertices on the actual objects here. The Graph API inside of Cosmos DB uses a language called Gremlin, And Gremlin is something that came out of the Apache Foundation, and it's primarily used in Node4.js. Is one of the popular implementations if you want to run your own server. But Gremlin is it's a query language that it's kind of takes a little bit of getting used to, but it's basically gives you the ability to query based on vertices and edges, where a vertice query says contains you start with an origin and then you kind of work out from that origin. You can say I want to start with all the vertices that have the city that starts with the letter A, and then I want to know all the roads that I want to know all the cities that are connected by interstates from all the cities that start with A. So your query would essentially say, first, give me all the cities that start with A, then find me all the cities that are connected by a vertice that represents a road that is connected to, and that vertice would be an interstate connection. And I want to know all the cities, say Atlanta, that are connected to Atlanta by way of an interstate that's represented by vertice. So that would be one use case for the way that this works, and that's how you kind of start with your query. You start with a vertice and you kind of work out from that vertice. So some supported languages and frameworks. This applies not to specifically to document databases. I'm sorry, to Gremlin or to the Graph API. You can use Node.js, .NET, Python, Java, REST, and SQL. You can pretty much use any major development environment you want to use, and it will work with any of the major paradigms that are available on Cosmos DB. And if you don't if there's not an SDK available, there's always REST APIs available that you can just call by way of HTTPS. And if you need to make queries against it, you can just form an HTTPS query and call that API endpoint, but using just HTTP protocol. It's a little bit more work, but the SDKs kind of take that edge off and make it a little bit easier to do. So I want to look at a demo that's using some of the .NET that uses the .NET API for the graph database. So this demo is it's fairly it's kind of a I'm gonna say it's an involved demo. So I'm gonna flip over to my IDE here. I'm using let me pull this over to Cosmos DB here. This is a .NET API, so I'm assuming that maybe you have a .NET. I don't know that you have a .NET development background, but this is basically using a Web API controller. And this Web API controller, this is the wrong demo. Let me pull up the right demo here. I'm glad I caught that before I actually tried to run that because it wouldn't worked. This one. Here it is. This is it. Now you can see here. This is a web API. It's a controller for Web API, and basically what I'm doing is I'm importing. I use the NuGet package within this application to import the libraries that I'm using here. So I'm using this Gremlin.net structure IO graph.json, and I'm using the Gremlin.net driver here to do my HTTP queries with. So these are native. These are .NET APIs that are available in NuGet, so you can just include these. And once you include these, then you can start querying your database. In this particularly this one, I'm using the Graph API, and whatever you're doing would be very similar to this, regardless of the paradigm that you're using in Cosmos DB. And most of the time, you're gonna wire up some kind of connection to that database. So it's going to be, you're going to specify the host name. You're going to specify the port that you're going to use. You're going to provide an auth key. This is typically a key that you find in the Azure Portal. And you're going to specify what database and the collection you're going to be using. And depending on how you set your database up, depends on what collection you're going to be using. I'm calling mine Thailand because I have a data set that has all the airports in Thailand in it. And I've linked all the, and because I'm using the Graph API, what I'm doing is I'm representing each airport as a vertice and each edge as a route that is flown between those airports. I'm going to show you this app in a minute, and you'll see how the Graph API does a great job at framing that up. And here's how I'm connecting to that. I'm using the database slash DBS, database slash collection. So my database is called Airport and my collection is called Thailand. So in Cosmos DB, you define everything around a database, and inside of a database, you have a collection. And so this one's expecting the username to be some combination of the database and the collection because I'm using the Gremlin server. I'm using the Gremlin API, and my password is the auth key for that. And I'm forcing it to use SSL over port 443 and my host name. And once I wire that up, I get a Gremlin client. And then when I call queries, I just simply create this query right here, and I call the Gremlin client, and I get back some data from that, and I just basically return it whatever it returns to me as a data set back to whoever calls this. So with that in mind, let me go ahead and start this application and kind of show you what it does. And I have a lot of different APIs that are doing different queries. So this one's basically saying, give me an airport and it'll give me the details for it. This one's telling me, give me a list of all the airports. Give me all the vertices that have a label of airport. And so it's saying all the vertices that have a label called airport. This one is telling me, get all the destinations where this is a Gremlin query here that says, give me all the vertices that have the vertices where the origin is what I pass in as a parameter here, right here, and then follow the outgoing edges, and then get me the incoming vertices. So it's basically anything that has that is connected to this airport right here with an IATA code of for Atlanta's ATL or for Charlotte CLT or something like that. So that's what this is doing. So that's what this query is doing. I'm just returning the results back as JSON data. So, and here's my consuming application. It's just a simple single page application where I'm doing some queries against this, and then populating a Google map with the results of the values, and it's using the map API from Google. So let's go ahead and start this guy up, and I'll show you what this looks like. So here is it's going to give me a 404 right now because I didn't specify index. And here's my map. And the first thing it did is it went out to Google, it loaded the Google map, it called my API endpoint. My API endpoint then went and queried Cosmos DB, pulled back all the airports, all the vertices that had a label of airport, and then it gave me the lat long of those airports, and then I used that lat long to drop a pin onto this map. So that happened pretty quickly. That query was pretty performant. So with this little demo app here, I can click on any app and it'll do another query against the database, and it will give me all the airports that connect to this particular airport that this airport flies from. So there's a route that goes from this airport back to an airport in Bangkok. So if I click on one up here in Chiang Rai or Lumpang or Nan, these will almost always link back to Bangkok, so because that's kind of the Grand Central Station of Thailand. And you can see if I click on the Bangkok airports that it will. There's two of them. There's Don Muang and Suvarnabhumi in Bangkok, and that way, and it kind of links to all the other airports inside of Thailand. Or I can click on the one up in Bai or the one up in I forget what that city is. Mang Son, and it will connect to Chiang Mai or what have you. So basically, this is just using those APIs to query the airport's routes that are represented by those vertices, and each of those edges, and then the vertices represent each of the airports. So again, using Cosmos DB to back this up. So this particular application is just using one of the paradigms. There's paradigms for documents for Cassandra and for key value stores as well. So I do have a little bit of content left. Go back to the deck here just to talk a little bit about pricing and performance. This is an important concept as well, and because the unit of measure on Cosmos DB is called an RU. It's a resource unit or request unit. Request units per second is how it meters it. And an RU is basically a function of compute, memory, and data, and it's kind of weighted towards the compute side of things. And it's basically the CRUD operations that you do on your data, and the request units are the scale unit that you have on Azure. So the more request units that you have, the more you pay for on Azure. Typically, writes are more intensive than reads, so they take more RUs. So relaxed consistency uses fewer RUs as well. So again, going back to that eventual consistency, if you want to keep your cost down in Cosmos DB, relax your consistency, and then you will use fewer RUs. And as that data replicates across the nodes, then you will see less RU used as well. Stored procedures, triggers, and UDFs use it. And there's two different tools on Cosmos DB for planning it. So here you can, with this capacity planner, you can go out to this capacity planner and you can upload a document to Cosmos DB to this capacity planner, and it'll give you a relative score what it thinks of how many RUs you think it thinks you will need. And then you can take that number that capacity planner gives you and plug it into this pricing calculator, and it will give you a relative cost of how much you think your spend is going to be for Azure Cosmos DB. So the combination of these two will kind of give you an idea of what it's going to cost to run Cosmos DB. And lastly, I want to mention some common features. I just want to throw this because I always get asked, what about security? It pretty much meets every security requirement you can throw at it, because this is available not only in the commercial cloud, but it's used in Azure Gov as well. And so if it meets the Azure Gov requirements, usually it's going to meet all of the requirements that are imposed on the Azure, on government agencies for HIPAA compliance or ISO specs or whatever the European model clauses, the UMAMC, and any other the DOPR requirements that are coming out of the EU and other things like that are required for compliance issues in whatever geography that you're in. And all of this stuff is important for some people that are concerned about security. I like the fact that it kind of obfuscates all this away, so I can pretty much say if I'm using Cosmos DB, I'm going to be able to take advantage of all these. However, I will caveat that with say it's a shared responsibility. While Microsoft provides all the security features for compliance and so on, it's up to you to maintain the identity and access management to that. So it's up to you to maintain who has access to your databases, who has access to your resources that are running on Cosmos DB. That's not just true of Cosmos; that's true of all of Azure and of or any cloud for that matter. So, any questions, comments, concerns about Cosmos DB? I know this is a lot, and I feel like I'm an auctioneer because I've been going a mile a minute. But again, I've only glossed. We've been going for a solid 45 minutes here, and I've only began to touch the surface of what Cosmos DB can do. So any comments, questions, or concerns about what Cosmos DB can do or anything like that? If you like this content, please consider visiting us online at www.wintellect.com, and there you can find about services that Wintellect offers, including training and consulting services. Also, please consider subscribing to this channel by clicking on the subscribe button and clicking the bell icon to get notifications when new content becomes available, and also comment down below. You can also follow me on Twitter at @TheOneMule, and also follow Wintellect on Twitter at WintellectNow or at Wintellect. We are constantly posting things about Azure-related technologies and things related to software development. You can also reach us by email at consulting@wintellect.com. Until next time, thank you.